question. Consider two different generative model based algorithms. In model 1, we have the assumption that chances of occurring a feature, it should be actually a feature occurring instead of occurring a feature. So the chances are affected by the occurrence of other features, and the model does not impose any additional condition on the conditional independence of features. So this is a very tedious way of saying that the features are dependent. Okay, so this means that the features are dependent. And in the second case, in the second model, it means that the features are independent, right? So what we essentially have to do, we have to see which of them has more number of parameters to estimate. Right? So let's understand this problem with a very simple example. Let's consider the example of binary classification. Okay, so binary classification means that the prediction that we will give y will be either 0 or 1, right? Or true or false, spam, non-spam, right? It is binary. At the same time, we also assume that the features are binary, which means the features x or xi, they are of the form 0, 1, power 2. Why 2? Because we are assuming there are two features, right? In general, this would be r power d. It can be r power d or 0, 1 power d, anything that sort, right? Okay. So here I have noted down all possibilities of zeros and ones that can ever occur, along with all possibilities of the labels, right? So this actually pertains to every data point that we will ever have will look like one of these rows. Okay, so that is ideal. And what is our what is our objective? Our objective is to create or to estimate the probability of seeing this data point, say x1, x2, given y, right? So so we have to estimate these probabilities, right? So once we estimate these probabilities, right, then given a new test data point, we can say, okay, which one has high probability? That will be our test label. Okay. Okay. So let's see how to estimate these probabilities. Okay. Suppose we want to estimate these probabilities. Okay. Then let me call these probabilities, say P1, P2, P3, and P4. Okay. Now, one thing to be noted is that these four probabilities will always add up to 1, right? So P1 plus P2 plus P3 plus P4 will always be equal to 1. Why it will be equal to 1? Because given y equal to 0, these are the only possible values of x1 and x2 that you can ever obtain, right? So they actually form a mutually exclusive and exhaustive set, which means the sum of the probabilities will be equal to 1, right? Similarly, we can also say that in the second case, right, where y is equal to 1, there also the probabilities will sum to 1, right? But before going to that, let me make one more note that if we want to estimate P1, P2, P3, P4, we only have to estimate P1, P2, and P3. Why? Because P4 can be automatically deduced as P4 equal to 1 minus P1 plus P2 plus P3. So essentially, we have to estimate only three parameters out of P1, P2, and P3. Now, similarly, we will have parameters, say Q1, Q2, Q3, and Q4, right? Which we will have to estimate. Again, the sum will be equal to 1. So Q1 up to Q4 is equal to 1. So Q4 can be estimated as 1 minus Q1 up to Q3. So again, from out of these four, Q1, Q2, Q3, and Q4, we have to estimate only three because the fourth one can be automatically reduced, right? Okay, let me write that down. So the number of parameters to be estimated is equal to 4 minus 1 plus 4 minus 1, right? That's how we obtained it. 4 minus 1 plus 4 minus 1. Now, how did we get 4? We got 4 because 4 is the number of possibilities of having x1 and x2, right? Because it is binary, we are having 2 power 2 because each possibility is 2 and there are two features, right? So we can write this as 2 power 2 minus 1 plus 2 power 2 minus 1. Okay. In general, this is taking the form, say, k power d minus 1 plus k power d minus 1. What is k? K is the number of data points, or you can say the values, number of values that a feature can take, and d is the number of features. So again, when I'm saying k is the number of values that a feature can take, I am referring to a problem where features can take only finitely many discrete values, okay, not continuous values. Although in continuous case we will have a different scenario, okay, it's called the Gaussian Naive Bayes. We'll discuss that later, okay. All right, so this is the general case, right? Now, uh, so so ultimately, how much do we have? We have 3 plus 3, which is 6 parameters, right? Which we have to estimate. Okay. Okay. So this is the case where we are not having any assumption, right? We are not assuming that the features are independent. We are assuming that the features are dependent, right? Okay. Now let us simplify that by saying that suppose we make the very critical assumption. So this is the most critical assumption of naive Bayes, right? Critical assumption. And what is it? It is that the probability of xi comma xj given y can be written as probability of xi given j, sorry, xi given y multiplied by the probability that xj given y. Now, what does this mean? This means this is the critical assumption of conditional independence. So, conditional independence of features, right? So this is conditional on which class we are referring to. That's why we have a conditional y, right? Okay. Note that this is not the same as saying that the features are independent, because this is a very common misconception that in naive Bayes feature should be independent. No, that is not the case. We need conditional independence, right? Okay. If you want a video on why they are different and examples on why where you can use independence, where you can use conditional independence, let me know down in the comments below. I'll make a separate video on that. Okay. Okay. So now, again, let's come back to the problem of discussing, uh, okay, how many parameters will be required to be estimated. Okay. All right. So now, when we have this additional assumption, right? So we have this additional assumption which says that they are independent, right? What does that mean? That means that we have to find out probability that x1 equal to 1, okay, given y equal to 0, right? Probability that x2 equal to 1 given y equal to 0. Similarly, probability x1 equal to 1 given y equal to 1, and probability x2 equal to 1 given y equal to 1. Right? Now, let me name these probabilities as P11, P12, or sorry, let me name this P21. This is again, so this should be Q11 and this is Q21, right? Okay, let me erase this part. So now the whole advantage of making this additional assumption, right, that the features are conditionally independent is that instead of P1, we can replace P1 by 1 minus P11, okay, 1 minus P11 multiplied by 1 minus P21. How did I do that? Because probability that, so what is this? What is P1? Okay, what is P1? P1 is, let me write it somewhere here. P1 denotes the probability that x1 is equal to 0, x2 is equal to 0, given y is equal to 0, right? Now, by this assumption on conditional independence, we can write this as probability x1 is equal to 0 given y equal to 0 multiplied with the probability that x2 is equal to 0 given y is equal to 0, right? Now, what is the first one? The first one is nothing but 1 minus probability x1 is equal to 1 given y is equal to 0, right? Multiplied with 1 minus probability x2 is equal to 0 given y is equal to 0, which is nothing but, according to our new notation, this is equal to 1 minus p11 multiplied by 1 minus p21, right? That's how we wrote that, okay? Similarly, we can write p2 as 1 minus p11 multiplied by p21, and p3 can be written as p11 times 1 minus p21, and p4 can be written as p11 multiplied by p21. Along the same lines, we can write q1 as 1 minus q11 multiplied by 1 minus q21, and so on. Okay, you can fill up the rest. It's the same pattern. So what happened now? So instead of p1, p2, p3, p4 that we initially had, and q1, q2, q3, q4, we only need two of them, right? So we only need four of them. In fact, p11, p21, and q11, q21, right? So that is the whole advantage. So now let us look at the parameters to be estimated. So number of parameters to be estimated with the assumption of conditional independence, right? What is that equal to? That is nothing but 2 plus 2, right, which is 4. That's it. Now, in fact, there is one more parameter which we had to estimate, which is that probability of y equal to 0 and probability y equal to 1, right? So they will be of the form, you can write it as p and 1 minus p. So this is one more parameter that we have to estimate. But this parameter that we have to estimate is the same for both model 1 and model 2. So we don't have to compare it separately. Okay. All right. So ultimately what we got only 4 parameters. So instead of 6 parameters that we had without the assumption, right? Because of the assumption, we are able to uh, write the joint probability as product of probabilities, and hence we require only 4 parameters to be estimated, right? So basically, which model has more parameters to estimate? The first model. Okay, so this should be independent. Okay, features are independent. So when features are independent, we have lesser parameters. So which model has more parameters? Model 1, right? So here's the question: which of the following statement is correct in the context of naive Bayes classification algorithm for binary classification with all binary features? So there are two ideas here. First is binary classification, all binary features, which means essentially that our y that we want to predict is binary, right? And all the x's are binary. In fact, we can write the feature space as 0, 1 to the power d, right? What is d? Number of features. So d is the number of features. Okay, fine. Pjy hat denotes the estimate for the probability that the jth feature value of a data point is 1, given that the point has label y, right? So let me write that down explicitly what they say. So pjy hat, okay, right? So this means this is equal to the probability that the jth feature is equal to 1 given the label capital Y is equal to small y, right? this is the probability, right? So this is what in fact these are the parameters that we estimate in naive Bayes, right? Okay. So what does the first option say? The first option says that if pjy is equal to 0.2 for y equal to 0, then it is equal to 0.8 for y equal to 1, right? So let me write that down. Okay. So what they are saying is that probability that xj is 1 given y is equal to 0, this is equal to 0.2, then that implies that the probability that xj is equal to 1, right, given y is equal to 1, this is equal to 0. This is not true, right? Because they are actually independent. Okay, why they are independent, we will see that. Okay, in fact, we can have any number instead of 0.8. Okay, so this can be 0.2 also. This can be any number. Okay, let us try to understand this with the help of an example. Okay. Okay, so let's consider a very simple example. Okay, simple example. So what is so simple about this example? It's that there we will take only one feature. Okay, so let's take one feature, xj or x1. Okay, x1 is the only feature, and we have y. Okay, and suppose we have these data points 1 0. Okay, 0 0 0 0, again a 0 0, again 0 0. Okay, so these are the data points we have, and then we have one data point which is 1 1 0 1. Okay, again 1 1. Okay, something like that. Okay, we can random data points, right? So why I wrote so many zeros here? The reason being that now what will be p1? So this one denotes the feature. Okay, the j p1 y equal to 0. Okay, hat. What will this be equal to? This will be equal to nothing but how many times 1 is occurring in the data set of label 0. So this is the whole data set of label zeros, right? In this data set, how many times 1 is occurring, right? That is the idea. So now we have that it will be nothing but 1 divided by how many are the total? There are total of 5, right? So that will be 1 by 5. Let me write that down. It will be 1 by 5, which is equal to 0.2. So this is why I created so many zeros, okay? In order to make it 0.2. But on the other hand, what will be p1 of y equal to 1 hat? This is equal to nothing but 2 by 3, right? So there are two ones out of 3 data points. So this will be 2 by 3, which is equal to, somewhere around, say, 0.66, right? Now this is definitely not equal to 0.8. In fact, this can be any number, right? We can construct this, the second part of the data set, however we want, right? So these elements have no influence on these elements, right? So they both of them are independent. Okay. Okay. So that is the idea, which means the first option is not true. Okay. All right. So we've understood why the option is false with the help of an example. Now let's look at the second option. What does the second option say? The second option says that probability jy, right, hat, and sum over all the features, right? So when we are saying summation j equal to 1 to d, that means sum over all the features. Okay. So sum over all the features, it should be, they're saying it should be 1, right? Now let's look at our simple example. Is it equal to 1? Okay, let's see. Okay, so here, okay, here there is only one feature. Okay, but let's add one more feature, say x2. Okay, and here we add the same data. Okay, 1 0 0 0. Okay, and here let me add, say, the same thing. Okay, 0 1 0. Okay, something like this. Right? So what they are saying is that, so what is p2 y equal to 0 hat? This is equal to, again, 1 by 5, right? 0.2, right? So now they are saying, according to their claim, the summation j equal to 1 to d, where d is 2 here in our simple example, pjy hat, which is equal to 1 by 5 plus 1 by 5, right? So that will be equal to 2 by 5, right? which is definitely not equal to 1, right? So we have constructed an example for which the second example is false. Remember, in mathematics, whenever we want to prove something is true, we have to prove it properly for all cases, right? In a general case, we have to prove it. On the other hand, if we want to show that a statement is false, it is enough to produce a counter example, right? So this is our counter example, right? This data set acts as a counter example for both the first option and the second option, okay? So that's why you can conclude that the first and the second options are false. Okay. What does the third one say? The third one says that if a particular probability is 0 for y equal to 0, then that will be 0 for y equal to 1. This is definitely not true, right? Let's again try to understand it with the same example. Okay. Let me modify the data set a little bit uh, and say that, let me modify the data set and say that this is equal to, or let me write this. So when y is equal to 1, we have say only zeros in x1, okay, in x1. Okay. So this means that pj or p1, okay, y is equal to 1 hat is equal to 0, right? But p1 y is equal to 0 hat is not equal to 0, right? Because this is equal to 0.2, right? So again, we have a counter example where the third option also fails. Okay. Now what does the fourth option say? The fourth option says that if pj1 is 0, no label 1 example takes the jth feature value as 1. Okay. So what is pj1 hat? Okay. This is nothing but the probability, the estimate of the probability that xj is taking the value 1, right, given y is equal to 1. Okay. What does this mean? So what will be the estimate? The estimate will be the fraction of data points having xj is equal to 1 out of the data points in class 1 or in class y is equal to 1, right? Okay, and if this is 0, what does that mean? That means there is no data point which has xj is equal to 1 in the class of data points having y is equal to 1, right? And that is exactly what the option says, right? Which means the the fourth option is correct, okay? And none of the above is here. The question says, if a test point was predicted to have the label 1, which of the following expression should be sufficient for this prediction? Okay, so this is essentially a straightforward question. Okay, so to understand and solve this question, we need to know what is the criteria when for a new test point or a new data point, an unseen data point to be classified, right? So what essentially what we need to know is the prediction criteria, right? For the prediction method for naive Bayes. Let me write this as NB. Okay. So given a new data point, right? Let me denote the new data point as say, uh, you know, okay. Let me denote it by f1, f2 up to fd, right? This is my x, okay, and the label being, so label has to be predicted, okay, fine. So this is my new data point, okay. All right. So the first option says, okay, this is bullshit. I don't know who said this paper, but yeah, this does not make sense. Okay. All right. Now, uh, what happens in naive Bayes? We try to understand which of the following probabilities are larger than the other. Okay, let me write that. So the probability, right, of probability that y is equal to 1, right, given x, right, given x. What is x? This is the new x, okay, the one which we got. Okay, let me write this as x new or x and x new. Okay, we want to compare this probability against versus this probability, right? probability y is equal to 0 given x new. Okay, so these are the two things we want to compare. Okay, now using Bayes theorem we can say that this particular guy on the left is proportional to the probability of x new given y is equal to 1 multiplied by the probability that y is equal to 1, right? And on the right hand side this guy is proportional to the probability of observing x new given y is equal to 0 multiplied with the probability that y is equal to 0, right? Now in by Bayes rule we will also have a denominator term, but that is independent of uh, y, right? So we can ignore that, okay? Because we are essentially comparing, right? So that term will be the same on the left and it will be the same on the right. So there is no effect, okay? So now on the left I can write this as equal to, see, we are by the assumption we are using in naive Bayes that the features are conditionally independent, right? That in that case we can say that this is nothing but the product of the features, the product of all the probabilities, because since they are conditionally independent, we can write the joint probability as the product of the probability. So this was done in, I guess, in some previous foundation courses. Okay. So the probability that xj, the probability of observing that xj. Okay. So let me write xj equal to fj. Right. So here fj denotes the value that the data point that we have. Okay. And that is so this whole thing is multiplied with probability y is equal to 1, right? Okay, I forgot to write down, it's conditional. Okay, so I have to write conditional on y is equal to 1, right? And this guy is multiplied with probability y is equal to 1, right? Similarly on the right hand side also we can write product, and for the product it will run over all the features, right? So j equal to 1 to d, there are d features. Again on the right we write j equal to 1 to d probability xj is equal to small fj given y is equal to 0, right? And this whole guy multiplied with the probability that y is equal to 0. Okay. Now, what will this be? Okay. So instead of writing, and this is actually the notation for what? This is the notation for this probability term. It can be written as nothing but pj1, right, hat to the power fj multiplied by 1 minus pj1 to the power 1 minus fg. Now one might think, okay, how did we write this, right? So, so what is the idea? So what is pj1 first of all? What is pj1? Pj1 is the probability that xj is equal to 1 given y is equal to 1, right? Now this means that the fj is equal to 1, right? So if fj is equal to 1, then we have pj1. But what if fj is equal to 0? That is this guy, xj equal to 0 given y is equal to 1, right? And in this case we write this as 1 minus pj1 or 1 minus pj1 hat. Okay, this is the estimates. Okay, so if fj is 1 we need this guy, and if fj is 0 we need this guy, right? So this together can be written as pj1, right, hat whole to the power fj, right? Because if fj is 1 we will get this, right? And if fj is 1, this particular term, the second term, okay, this term will be equal to 1. Sorry, this should be, just a second, it should be 1 minus fj. Okay, let me write that clearly. This has to be 1 minus pj hat to the power 1 minus fj. So if fj is 1, this term becomes 0. Sorry, not 0, it becomes 1. And then, and you have only pj1 hat, right? And on the other hand, if fj is 1, on the other hand, if fj is 0, then this term becomes 1, and this term will be equal to 1 minus pj1 hat. Okay, Alright, so that is the whole idea of representing this term as pj1 to the power pj1 hat power fj multiplied with 1 minus pj1 power 1 minus fj. Okay, so this is nothing but product of all these guys, j running from 1 to d, and then this is multiplied with probability y is equal to 1, right? So similar thing we will have on the left hand side, right hand side, right? We will have probability j0, right, whole to the power fj 1 minus pj0 hat whole to the power 1 minus fj, product over all features j running from 1 to d, and then multiplied with probability y is equal to 0. Right? So essentially, if we want the prediction to be 1, we need this probability to be bigger, right? The probability on the left should be bigger, and this is exactly what the third option says. Okay, that is the correct one. Right, so here we have a problem with only one feature, and this is a Gaussian naive Bayes problem, right? So what does that mean? That means we assume that the data points given the class are normally distributed, right? Okay, and furthermore, it says that the decision boundary is linear. Then what will be the value of sigma square? Okay, let's try to find that out. But before that, let's recall what the Gaussian naive Bayes says. So it says that since it is normally distributed, the PDF will look like something which is given on the screen. Okay, 1 by sigma under root 2 pi e to the power minus half of x minus mu by sigma whole square. Note one minute thing, which is that sigma depends on y, mu depends on y. Okay, and again here sigma square depends on y. Okay, fine. So and there is a very important theorem which says that the decision boundary is linear if and only if. So this IFF stands for if and only if. Okay, if and only if the variances are equal for both the classes. And we will try to prove this result, okay, mathematically. Let's do it step by step, okay. So what is the decision boundary? So the decision boundary, let me write that down. The decision boundary is nothing but, what is the decision boundary? Is nothing but the probability that y is equal to 0 given x, right, equals to the probability that y is equal to 1 given x. Now, if one of them is greater, that particular class will be predicted, right? So this is where the boundary occurs, right? That is why we call this the decision boundary. Okay. All right. Let's continue. So this equality can be rewritten as again by using Bayes rule. We can rewrite this as probability x given y is equal to 0 multiplied with the probability that y is equal to 0, which is equal to the probability x given y is equal to 1 multiplied with the probability that y is equal to 1. Again, using Bayes rule. Okay. Now there is another term on the denominator which is probability x equal x, which is probability x. Okay, so this term, right? This is there on the denominator, but it's not important because they will get cancelled out, right? So this term is not important. Okay. So now if I take log on both sides, okay, let me take log on both sides, and then I can write this as logarithm of p of x given y is equal to 0. Again, what will this quantity be? This will nothing but this will be nothing but the PDF of Gaussian, which is this, right? See, one thing to note is that this is definitely not equal to the probability, right? But in case of continuous distribution, we use the PDF in place of the probability. Okay, fine. So we use the logarithm because see what we want to maximize in continuous distribution, we want to maximize the likelihood, right? Essentially, we want to find which data point has more likelihood. Okay. Okay. So let me make a note here. That note, in case of continuous distributions, we use PDF to measure likelihood. To measure likelihood. Okay. So this is as a note. Now let's continue with the proof. Now when I take log on both sides, again let me write this as f of x given y equal to 0, right? Plus log of probability y equal to 0. right? That is equal to log of f of x given y is equal to 1 plus log of probability y is equal to 1, right? Okay. Now what we can do is that we can substitute the likelihood. Okay. See, when we take log of this, what will we get? Let me take it here itself. Okay. When I take log of this, I will get, we can ignore the under root 2 pi term, right? Because anyway it will get cancelled from both sides. So we will essentially get 1 log of sigma y. Okay, so that will be minus log of sigma y. That will be there, right? And we will also have minus half of, okay, minus half of x minus mu y by sigma y whole square. Okay. Now, when I take product of all the data points available, right? So instead of uh, just log sigma y, we will have log sigma y whole to the power n, right? What is small n? N is the number of data points. Similarly, uh, here I will have, in the other side, uh, I will have a minus half here, and then I'll have the sum over all I running from 1 to n xi. Okay, that is the difference which will happen. Why is this difference happening? Because when we take multiple data points to obtain the likelihood, we take the product of the densities, right? Take the product of the individual densities. And why do we take the product? Because we assume that the sample is random and they are independent, right? So we can take the product. Okay, so this is the expression that we will get. Okay, fine. So let me substitute that right away here. So I can say that minus half of, right, and then summation I running from 1 to n, okay, xi minus, so mu y, instead of mu y I'll write mu 0 by sigma 0 square, okay, okay, uh, and then I will have a minus of log of, okay, log of, so log sigma y power n, that means minus n times log of sigma 0, okay, so instead of sigma y I'll write sigma 0, okay. And then again there is a log term, log of p of y, p probability y is equal to 0, right? Okay. Now that will be equal to, what will we have on the right hand side? The same thing, okay, the same expression with a few minute differences, which is that instead of mu 0 we will have mu 1, instead of sigma 0 square we will have sigma 1 square, and then I'll have a minus n times of log of sigma 1 plus log of probability y equal to 1, right? Okay. Now let me bring both the terms to one side. So I'll have, and let me get rid of the minus half, okay? So also let me take it outside. Let me just take it outside. So I'll have minus half, right? And then summation I running from 1 to n. We will have xi minus mu naught by sigma naught square, okay? Or sigma naught whole square, right? So, okay, this should be whole square, okay? Let me just make that correction. So this should be whole square, right? Sigma naught and sigma 1, okay, plus, sorry, minus, I will have xi minus mu 1 by sigma 1 whole square, right? Okay, so this is what we have. Now this and then we will have another term which is, let me write it as minus n times of log of sigma naught minus log of sigma 1, right? Then I have some probability terms. So this will be log of probability y equal to 0 plus log of, sorry, it will be minus log of probability y equal to 1. Okay. So this is also, this will be equal to 0. So this is the term that we have, right? Now we are concerned with only those terms which have xi's. So observe, we have an xi here, we have an xi here, right? This whole term, right? This whole term is actually a constant term, right? Does not matter much. Okay, now let us analyze the term which has the xi, right? See, when will this be? So this is generally what? This is generally a quadratic equation in xi, right? So in xi, this equation is quadratic. This equation is quadratic, right? But when will it be quadratic? It will be quadratic only if and only if sigma naught square is different from sigma 1 square, right? Because if sigma naught square and sigma 1 square are equal, then the coefficients corresponding to xi square will cancel out, right? Let me write that down. If sigma naught square is equal to sigma 1 square, then coefficients of all xi's will be 0, right? Hence making it a linear decision boundary. Okay, linear decision boundary. That is the idea. So we have proved that it will have a linear decision boundary if and only if both the variances are equal, right? Now let us apply this result here in our problem. So we can say that sigma square will be equal to 2 because we want both the variances to be equal. That is, here we have another binary classification problem with two binary features, right? F1 and F2. Again, they are binary features, which means F1 and F2 can take values 0, 1. Okay. Another thing which is given is that the F2 feature values are 0 for all label 0 examples, but the label 1 examples take both values 1 and 0 for the feature F2. Okay, let me write that down explicitly. What does it say? It says that if you look at the number of uh, data points, right? Number of data points uh, which have f2 equal to 1, right? Out of all data points, right? In class or instead of class, let me write label. In label 0, right? This is equal to 0. That's what this first statement says, right? Because it says that all data points have got the value f2 to be 0, which means f2 equal to 1 is 0, right? There are no data points which have f2 equal to 1, which also means that probability that f2 equals to 1 given y equal to 0, this is equal to 0, right? Okay. Now, how does prediction happen in naive Bayes? We look at two important probabilities, right? One is the probability that y equal to 1 given f1 and f2 is equal to 1 and 1, right? Why this? Because we are predicting for the point 1 comma 1, right? So f1 is 1, f2 is 1, okay? Similarly, we'll also compute the probability that y is equal to 0 given f1 is 1 and f2 is 1, right? And we'll compare these two probabilities, and whichever is bigger, that will be assigned the prediction. Okay, so the bigger probability, let me write that down. Bigger probability uh, will uh, receive the label. Okay, so if the green probability is bigger, then this particular point will be assigned the value 0. Okay, all right. So now we have another case. We are told that probability f2 is 1 given y equal to 0 is equal to 0. Okay. Now we can observe that this occurs somewhere here. Okay. So this is nothing but this particular value. Okay. So we are told that this particular value is equal to 0, right? This is equal to 0, which means this whole thing will be 0. Okay. So this probability will always be equal to 0. Okay. Now we are also told that the label 1 examples take both values 1 and 0 for the feature f2, right? Which means, what does this mean? This means that this guy, right, this guy here is non-zero. In fact, this is strictly positive, right? Because it takes both values 0 and 1, okay, right? So we know this is positive, okay? But we do not know if this particular value, this one, the first one, which is probability f1 equal to 1 given y equal to 1, if this is 0 or not. Because if this is 0, then both will be 0, right? So let me write that down. If probability f1 equal to 1 given y equal to 1 is equal to 0, then both probability y equal to 0 given x and probability y equal to 1 given x will be equal to 0. So hence we have a tie. Hence we have a tie. Now what does that mean? That means that, and we are not given any tie breaking rule, right? So since we are not given any tie breaking rule, that means that we have got insufficient information to predict the data point. Again have a binary classification problem with two features f1 and f2, right? And it's given that the data points given the labels follow a Gaussian distribution, okay? And we are given the data set. So the first question says what will be the value of p hat, which is the estimate for probability y equal to 1, right? So this is nothing but, so we all know this is a straightforward question, right? So p hat, or the probability y equal to 1, is estimated as, so let me write it down. It is estimated as the fraction of data points, right? Data points which has label 1, which has label 1. And how is this estimation happening? It's happening through MLE, maximum likelihood, okay? So in fact you can write the likelihood function, try to maximize it by taking derivative with respect to p hat. You'll get exactly this thing, right? So this will be nothing but, so how many of the labels have 1? So that is nothing but 2 out of 4, which is nothing but 0.5. So the answer is 0.5, right? Okay. The next question says what will be the value of mu naught hat? Okay. So how is mu naught hat estimated? So mu naught hat is the mean of, so let me write mean of data points, data points which belong to, so which belong to class 0 or label 0, okay, or label 0. So which are the data points? We have 1.3 and 2.3, right? So if you take the average, you'll get 3.6 divided by 2, which is 1.8. Okay, so this is for f1. Okay, so this is for f1, and for f2 you'll have to take the average of 2.4 and 2, which is nothing but 4.4 divided by 2, which is 2.2, and this is f2, right? Okay, so the value of mu naught hat will be 1.8 comma 2.2. Okay, so this is the answer. We have a binary classification problem, two features f1 and f2. Okay, so let me write that down. We have f1 and we have f2 and a label y. Okay, so it says the feature f1 is categorical, which can take three values. So f1 can take three values. Okay, let me call that what? Let me call that 0, 1 and 2. Okay, all right. And the feature f2 is numerical, that follows Gaussian distribution, right? And the question says how many parameters must be estimated if we apply the naive Bayes algorithm to the same data set. Assume that the covariance is the same for both the distributions, f2 given class 0 and f2 given class 1. Okay, so the first thing we can say is that f2 given class 0, which is f2 given y is equal to 0, follows a normal distribution with mean say mu naught and sigma and variance sigma square. Okay, similarly f1 given, sorry, not f1, it should be f2 given y is equal to 1 follows normal mu1 comma sigma square. Again these sigma squares are the same. Okay, all right, so this is the assumptions corresponding to Gaussian distribution, which is feature 2, right? What about feature 1? For feature 1 we can say that we have to find the probabilities, right? We have to estimate the probability that feature 1 is equal to 0 given y is equal to 0, right? We also have to estimate the probability f1 is equal to 1 given y is equal to 0, right? From, if we get these two probabilities, we can easily obtain, we can obtain the third probability, which is probability f1 is equal to 2 given y is equal to 0. So this is not to be estimated. We don't have to estimate this. We only have to estimate these two probabilities, right? Okay. And similarly, uh, so this is what we have to, and similarly for y equal to 1 also we have to do the same thing, right? So probability f1 is equal to 0 given y is equal to 1, and probability f1 is equal to 1 given y is equal to 1. So these four probabilities we have to estimate, right? So essentially there are four parameters here, right? And then there is uh, mu0, mu1 and sigma square, right? Okay. So how many parameters do we have now? So seven parameters as of now. Okay, seven parameters. Now, apart from this, we also need to estimate the probability that y is equal to 1, right? We usually uh, denote it by p hat, okay? Because once we have this, we can obviously obtain the probability y is equal to 0. So this can be easily obtained. So p hat is also there. So 7 plus 1, which is equal to 8 parameters in total. Okay? So the answer is 8. A binary classification data set with 1000 data points belonging to 0, 1 square, right? So this means that what does this mean? This means that we have two features f1 and f2, right? That is why the feature space is, so the feature space is represented as script f, which is nothing but 0, 1, 2. Okay, fine. And the naive Bayes algorithm is run, and we already have the estimates here. Okay, the question says what is the estimated value of probability f2 equal to 0 given y equal to 1. Okay, now this we know that the probability that f2 equal to 0 given y equal to 1 plus the probability that f2 equal to 1 given y equal to 1 will sum up to 1, right? Because they are mutually exclusive exhaustive events, right? So given y equal to 1, either f2 can be 0 or f2 can be 1. Okay, think about it this way. So what is this? This is nothing but 1 minus, see this guy is already provided, f2 equal to 1 given y equal to 1, which is 0.02, right? So 1 minus 0.02, which is equal to 0.98. That is the answer. Okay. The next question says what is the predicted label for the data point 0, 1? Okay, let's see. So what does this mean? This means f1 is equal to 0, f2 is equal to 1, right? Now we have to compute two probabilities. One is the probability that y is equal to 0 given f1 is 0 and f2 is 1, right? So this is proportional to what? This is proportional to probability f1 is equal to 0 given y equal to 0 multiplied with the probability f2 is equal to 1 given y equal to 0 multiplied with probability y equal to 0. Right. Now we are able to write this using the conditional independence of features, right? Or more precisely, the class conditional independence of features. Okay. Now we have these values, right? So the first one would be f1 equal to 0 given y equal to 0. That would be 1 minus 0.2. So this guy is 1 minus 0.2. Okay. What is this guy? This guy would be 0.3. Okay. So this guy would be 0.3. And probability y equal to 0 is given to be 1 minus 0.3. 1 minus 0.3, which is 0.7. Okay, so this is nothing but 0.8 multiplied by 0.3 multiplied by 0.7. What is this equal to? This will be equal to, let me just calculate it, 0.7 multiplied by 0.3 multiplied by 0.8, which is 0.168. Okay, now we need to compute the second one, which is probability y equal to 1 given f1 is 0 and f2 is 1. Now this is proportional to the probability that f1 is 0 given y equal to 1 multiplied with probability f2 is 1 given y equal to 1 multiplied with the probability of y equal to 1. Now probability y equal to 1 is nothing but 0.7, sorry, 0.3, right? This guy, probability f2 equal to 1 given y equal to 1, that is equal to 0.02, and this guy is nothing but 1 minus of 0.1, which is, so this is 1 minus 0.1, right? So we have 0.9 multiplied by 0.9, sorry, multiplied by 0.02 multiplied by 0.3. So what would that give us? 0.9 multiplied by 0.02 multiplied by 0.3. That would be 0.0054. Okay. Now definitely this is larger, right? This one. This is larger. So we can say that the label which is assigned to this point is y equal to 0.